Hello and welcome to this video. My name is Tim. I'm online known as Timendous. And in this video, I'm going to talk to you about CHIP-8, and I'm going to show you how to make a game something like this. So where I can dodge asteroids. I'm really bad at this game. It requires reaction times, which is not something I'm very good at, but you get the point. It's a fun little game, and we're going to look at this game, see how it's made, and how we can make something similar to this. But first, let's talk a bit about why I'm making this video. Octojam is coming up. Octojam is the yearly thing where a bunch of people come together and make games for the CHIP-8 platform, and the 9th edition is coming October, so that's next month. You may be watching this in the future. The value of the video is still the same. Nothing much changes in this platform because it is a system from the 70s. Also, I didn't find any videos on YouTube talking about how to make games for the platform. There are thousands, if not tens of thousands of videos explaining how to make an emulator or an interpreter for CHIP-8, but pretty much nobody talks about how to make actual games for this system. Like I said, it's a system from the 70s, so this is what the CHIP-8 system used to look like, right? So what's interesting is that both of these systems are running games in these photos. This is a very old photo. This is the actual computer. This is a tape drive, and this is the monitor. So this is the same computer. It's a very small computer. It's not very big. It has a very annoying little keypad here. This is the keyboard that you get. This is all just enough to be able to enter byte values, and that's about it. Now nowadays, we live in the 2020 somethings, and we can run CHIP-8 on pretty much anything. It's like Doom. It's not a matter of does it run Doom, it's just a matter of when does it run Doom. It's the same with CHIP-8. So I have this tiny little Game Boy-like console here. It's called a Thumbie, and it is running my my game from 2 years ago from Octojam called 3D Viper Maze on a CHIP-8 interpreter. So even something as tiny as this can easily run CHIP-8 nowadays, because it is such a simple system and is very slow as well. Okay, so how does it work? Basically, the idea is that you have a CHIP-8 game, and it runs on a virtual machine or an interpreter or an emulator. People use different terms for it, but it's basically mostly a virtual machine in my book. And the virtual machine then runs on the actual physical machine, on the actual platform that you're developing for, or that you're running it on. So you develop your game for the virtual machine, basically. So the upside is that if you want to run your game on a different device, on something else, you can just swap out the actual device. You can swap out the interpreter or the virtual machine or the emulator or whatever term you want to use, and you can still run the same game, which is pretty cool. And this is also the unique selling point back in the 70s, because there were a couple of these hobbyist computers, and there were very few people writing games for them. And CHIP-8 allowed hobbyists to use each other's games on different platforms. So the thing that I just showed you is the RCA Cosmac VIP, but that was not the only computer running CHIP-8. As soon as it got a bit popular and more games were being written for CHIP-8, it was ported to all kinds of other hardware from the era. All right. We're going to do some programming. I'm going to talk you through the game that I just showed you and talk to you about all the steps that you need to take to make that work, or something like that work. First of all, I'm going to share this link with you. This is the link to the IDE that we will be using today for this video. It is the IDE that most people use. It's also in the description below. So let's switch over to my browser window. We're not going to look at this game immediately because there is quite a bit of code here. I want to take you back, like way back first, to how would they do this in the 70s, right? In the 70s, we didn't have an editor on a computer because the computer couldn't run an editor. Like you just saw, it has a 16-key keyboard. There's no way you're writing code on that. So what you would do is you would take pen and paper and then write something like that onto paper. So I want to load a value hexadecimal A. I want to load that into a register, right? And we'll get to what registers we have available in a minute. Now, once you've written this down, your intent, like the steps you want to take, you would then hand assemble this into binary form or in hexadecimal form. So this is what you would actually enter into the computer. And that sounds very daunting, but it was quite possible because CHIP-8 is so simple, relatively simple. So the 6 here just means load some value into a register. Then the next value is the register to load it into, and the next byte is the actual value to load into that register. Right, so you can see the pattern here, load B into V1, load C into V2. So this is the value B to load into 1 and the value C to load into 2. And the first number doesn't change because the instructions are all the same. So these are all the same instruction up until here and there, and then we get a different instruction. So this is the way people used to do this, with pen and paper, or write down the instructions, then hand assemble them to actual values, and then enter those values into their Cosmic VIP. I can only imagine that this must have been an absolute pain. So what Octo allows us to do, that is the IDE that we're using today, is write the same code in a way that makes sense to the modern human, or at least the modern developer. So we can just say load the value hexadecimal A into the register V0, and you figure out what hexadecimal values this represents, right? And that is the role of the assembler, so to take a piece of code and to turn that into bytecode or machine code. So this is the first program we're going to be looking at in a minute, and this just shows ABC on the screen. So this is like the hello world of CHIP-8. But first I want to take you to the whiteboard for a moment. Because we need to talk about memory layout and registers. So this is the CHIP-8 memory layout. It starts here at 0 and it goes to FFF, which is not so much. It's like the 3.4K, I believe. So that's very little memory. It gets even worse because you cannot use the first 200 hexadecimal 200, so that's 512 bytes of memory, because this is where the interpreter used to reside. So on the Cosmic VIP, this was the space you had to store your game, and this was the space where the interpreter was stored. It gets even worse because this part on the original Cosmic VIP, like the end of memory, there was some space reserved for like the display buffer. The stack was here, things like that, right? So this is the space that you have for your program, which is about 32K. That is not a lot. That's even worse than you think. You run out of space in no time. I can tell you that. So it's good to know this because first of all, your program starts. So the program counter, the PC, the program counter starts at 512. That's where your program starts. So that is also where your program gets loaded into memory when you start a program on a modern interpreter. That hasn't changed in 50 years. And then the program starts running like sequentially down the line until it encounters like a jump or a call, and then it goes somewhere else, right? Your data also resides in the same memory space. So for example, if you want to have a sprite, let's say we have that little spaceship that you just saw in the game. That spaceship, that consists of a couple of bytes, and those bytes live, for example, here in memory. And then you may have a table or something, some other data that you want to store, and that table also lives here in memory. So what you then do is in your code, you point to somewhere else in memory, for example, to the sprite, and you say use that. And we have one register to do that with, and that is the I register. Let's move that down a bit. That is the I register, and that is the only, we call it the index register, that is the only register that is 16 bits, and that can actually index anything, right? So that can point to memory, which is a bit of a pain sometimes. So next to that we have 15 general purpose 8-bit registers, V0 through VF, or V15 if you prefer, that's also fine, if you don't like hexadecimal. And these are the 8-bit registers. VF is a bit special in the sense that it is also a flag register. So if, for example, I'm doing V0 equals V1 plus V2, I'm not even sure if this is a valid instruction. I don't think it is. I think that should be V0 plus equals V1, for example. So ignore this. So I want to add the value of V1 to the value of V0. Now, if that value, that resulting value, does not fit in 8 bits, then VF will be set to 1. And the interpreter does that for you. You don't have to do that. So you can then use that to check if your value overflowed or things like that. Right, so those are the registers that you have. You have 15 like real general purpose registers. Then there's a 16th flag register that you can also kind of use as a general purpose register, but be warned, that's kind of dangerous. You have one 16-bit index register, and there's a couple of special purpose registers. There's the delay timer, and usually you call it DT. The delay timer can be used to synchronize things. So what it does is you can say I want to store the value 5, for example, in my delay timer, and then every loop of the display, not of the interpreter, but of the display, that's 60 times a second, DT gets decremented by 1. So after 5/60th of a second, DT will be 0. And you can use that to say like V0 is delay in Octo. This should also be delay. And you can then load the current value of the delay timer back into a register and then look at it and see if it's 0 or something. So that way you can do some timing things that are timed to an actual clock instead of just the CPU frequency. And the final register, let's get some clear space here. The final register that exists is the sound timer. I'm going to call that ST. And the sound timer works pretty much the same as the delay timer in the sense that you load a value into the sound timer. Let's say 5 again. And then every 1/60th of a second, the sound timer gets decremented by 1 until it is 0. You cannot read from the sound timer, you can only write to it. But the funny side effect of it, and that is why it's called a sound timer, is that it will do a beep as long as the sound timer is unequal to 0. Right? So if you say 5, then it will beep for 5/60th of a second, which is very short. If you want to have a second beep, you say the sound timer is 60. All right. So that is pretty much all of CHIP-8. Let me zoom out a bit. This is all you need to know, except for, of course, all the instructions that exist. This is basically all there is to know. There's a memory layout of around 3.4K. There's a handful of registers that you can use for things. There's one index register, there's a delay timer, and there's a sound timer. And this is pretty much all you need to know. The only thing I have to add to this is that there are different versions of CHIP-8. Be aware of that. What I just explained to you is like the original CHIP-8 from the 70s. There's also a CHIP-8 from the 90s called SUPERCHIP, and there's a CHIP-8 from the zeros that is EXO-CHIP. Those generally have more memory. That is the main big difference. Those that have more memory. And EXO-CHIP also allows you to do more than just beeps. It allows you to actually play some tunes and some music. But we're going to focus on like the basics today, so I'm not going to go too deep into that. So let's now go back to this little program that just shows like the CHIP-8 Hello World on the screen, ABC. What does this program actually do? Let's just walk through it. It's not that hard, and I think you'll recognize a lot. For example, the registers, I'm using V0 through V6, so these 7 registers are in use in my program. I'm loading the values A, B, and C, hexadecimal values, into registers V0 through V2. And those are the things that we're showing on the screen. We'll get to how that works in a bit. And then I'm loading 4 additional values into V3, V4, V5, and V6, and those 4 additional values are actually the coordinates that I'm showing the characters on screen with. So if I change this to 10, it should move up, right? And if I change it to 20, it should move down. So those are the coordinates that I'm drawing at. Then we get to the actual code part. I'm setting the index register I here, and I'm setting it with the hex value of V0. What that means basically is that we're asking the interpreter to give us a pointer to font data for the value in V0, right? Which is a bit weird, but you have to understand this is not an actual computer, so this is an interpreter, and it can do things for you, and it can make things easier for you. And there are a couple of these kind of weird instructions that you would not see in an actual instruction set for an actual CPU. This is one of them. The next one is as well, that try to make your life easier. So what it does is it just gives you the address of a font that can represent the character A somewhere in memory, and you don't know where. Well, the answer I can tell you where it is actually. Let me go back to the whiteboard. It is somewhere in here. That's where it is. So we get I to point somewhere into the memory of the interpreter now, and what that allows us to then draw a sprite from that address, right? So I now holds a pointer to an address of a sprite. And then we do sprite. And what sprite does is it draws an image on the screen somewhere. Sorry for that. And it draws it at these coordinates. So V4, V3, so that's 23 by 13. So X is 23 and Y is 13. And then the 5 means that it will draw 5 bytes. That sounds weird until I run it again, and you see that 1, 2, 3, 4, 5. It has 5 lines, this sprite. Every byte in memory is drawn as a line on screen, and if the value in that byte is a 1, it shows a pixel that's on, and if the value is 0, it shows a pixel that's off. It's a bit more complicated than that, because it actually exclusive ORs with the actual existing display, which is something that you will definitely run into in the future, but let's skip over that for now because it's a bit much to explain right here. So we load a pointer to a font representing the value in V0, which is A, into our index register, and then we sprite that, then we draw that sprite at these coordinates for 5 bytes to the screen. So you see that sprite takes no argument of which sprite to draw. That is indirectly referenced by the index register I. So you have to set I before you can call sprite, right? And then we do the same thing with the other values. So we take the hex value of V1, which is B, and then we draw that at slightly different coordinates, so 29 by 13, and finally we draw the third value, which is C, at 35 by 13, and that draws ABC. Now before we continue, I want to zoom out a bit because Octo has a couple of very useful features here. It has a toolbox where you can draw sprites, for example. You can also do audio if you're doing ExoChip and you're doing something more interesting than those beeps that we talked about. Here under binary tools, you can download your program as a binary file, which is very useful. You can change the appearance. You just saw that this is these like brownish colors, that is these colors, and you can redefine the colors if you want. You can also change the font. So for example, if you didn't like the way that those that the ABC looked like, it's a bit boring, let's change that into a more interesting ABC. Use a different font. And then there's the options panel, where you can select a compatibility profile. That's the main thing here. I've set it to VIP compatibility mode because that is like the 70s original Cosmac VIP compatibility mode. But you can also choose SUPERCHIP or EXOCHIP here. And we're going to look at SUPERCHIP in a bit. But that changes all these things above here. So the size of the memory and the like special little quirks of the different systems. Also, I see I've made a bit of a boo-boo. I said 32K before. I meant 3.2K for VIP, like 3,200 bytes. That's even less than you thought. Alrighty, so the toolbox is excellent, and the manual is also excellent. If you are running into issues, if you don't know how to like how to put something into words, you can read through this manual, which is quite useful. This is all the statements that you have. So we have our sprite command here, for example. Let's draw a sprite at some coordinate, and then here we have all the assignments like the n equals hex vx that we just used. So this is a very useful manual, and yeah, make sure you look in this first if you're running into issues. All right, time to move on. Time to look at the game, at the actual game. So let's look at what the game does first. I have asteroids. The asteroids are falling down the screen somehow, so we have to make that. Then I have a ship, and I can move the ship with my cursor keys, but only left and right. And when I have a collision with one of the asteroids, I'm game over and I have to start again. So it waits for a key press, and when I press some key, it moves on with the game. So that is conceptually what it does. Now let's look at the code and see how John actually did this, because this is an example game from Octojam 8, from last year's Octojam. It's a very short piece of code. It's just 43 lines of code, including comments. So it's not very hard. And you're just going to go through it line by line, so you get a feel of what it means to be writing a CHIP-8 game. And John uses a couple of tricks here, and we're going to start off with one of those tricks. We start with a label, and the label here is main. And that is the point where the program starts. We have another label down here that is registers. And a label is just nothing more than a semicolon followed by some text, right? We have a couple more down here. We have a label called ship and a label called rock. Now, what John does here is he sets I, our index register, to the label registers, which is this one. So he points I into memory where these values are stored. And these values are commented, so we know what they mean. This is the ship X position, or at least, excuse me, at least the starting position. This is the ship Y position, and this is where we spawn our rocks from. So the asteroids that are coming down, they're coming down from coordinate 0 at the top of the screen, and they're coming down, right? So we spawn them at the top. And then there's 2 more bytes, and he uses this semicolon byte syntax for that, and then a value that Octo understands, which is the key definition. So A and D is left and right, and we load those into registers as well. And the way we do that is we point, we make I equal to registers, so I points to this space of memory, and then we say load v4. And load is one of a duo of instructions. There's load and there's save, or store. Save, store. This is where the manual comes in. Store, save, save. The word is save. So there's load and save. And what those do is they read or write registers to and from memory. Right. So I'm pointing to registers, and then I say load v4. What that does, it loads v0 through v4. So it loads these 5 values into the registers v0, v1, v2, v3, and v4. That's what that does. All right, so we've covered that. Then clear is what clears the screen. It just erases everything that's on the display. That's also quite easy. Then we go into a loop. Actually, we go into 2 loops. This loop ends here, and that loop ends there, as you can see from the indentation. But the indentation is optional, so Don't expect everyone to do that right. Let's start with the inner loop first, because that's easiest, smallest. Loops are a construct that Octo introduces, because CHIP-8 doesn't really have a concept of loops. It has a construct of jumps. In CHIP-8, you can just jump back and forth somewhere else in memory. Octo uses the construct of jump to give you loops, right? So what that basically does is loop here says this is the point where we're going to jump back to, and again is the keyword that jumps back to the corresponding loop. Now we don't always want to jump back up here, because then we have no program. It's just an endless loop, and it's stuck. So it's preceded by this. There's a then here. If VF, or our 15th register, is not 0, then we do that. So it only jumps back up to loop if VF is something other than 0. And why are we doing that? Well, we're doing that because we're reading the delay timer that I explained to you before. We're taking a look at the delay timer and seeing if it's 0. And if it's not 0, we jump back up. So what that basically does is it waits for a given number of frames before we're able to break out of this loop. And the number of frames that we're doing is actually the next two lines. So we're setting VF to 6 here, and then we're setting delay to VF. You have to do it in 2 steps. You cannot just do this, because there is not a valid CHIP-8 instruction to do that. So you have to load into a register first. So these lines together make sure that we're updating the screen, or we're running the code below, so updating the game state, only every 1/60th of a second. So that's 10 times per second. So 10 times per second we're going into the rest of the code, and this basically works like a frame limiter. Then we know that the outer loop, so this one loop and then down here to again, we know that that loop is running at 10 times a second, right? What do we do 10 times a second? First, we scroll down 4. And this is actually a SUPERCHIP instruction. This is not an original CHIP-8 instruction. It's a SUPERCHIP instruction that allows you to scroll the screen down. That just does exactly what you think it will do. It scrolls down the entire display 4 pixels, right? So that's done. Then we get a random value, some random value, and we're going to use that as the coordinate of the newly spawning asteroid. Right, so every frame we scroll everything down, and we add in a new asteroid, and we scroll everything down, and we add in a new asteroid. So the exposition of the asteroid that we're going to spawn is a random value. Now random does not work like random does in most other programming languages. So 63 is not the upper limit, but instead it is the bit mask. That is something to be aware of. So if we do this, then the program breaks, because 64 is something like, what is it? Something like that. Whereas 63 is something like that. Right? So you have to know your binary to be able to do CHIP-8. It helps a lot. What this does is it uses all the ones in here to and with a random byte. So we get a random byte, and we only take these bits, these 5 bits. And that's what this line is doing. So we get a value from 0 to 63, which is perfect because we have a 64 pixel wide display. So 0 to 63 is just right. Then we set I, our index register, to another label, the label rock. Now the label rock is down here, and it is followed by these bytes here. Now you may be wondering, well, what do those bytes represent? Well, we can look at that by copy pasting it into the sprite editor, and we see our asteroid, right? And we can change it if we want to. We can add some bullshit here. So there you go. Now it's an asteroid with an I next to it or something. And the same goes for the ship. This is the ship sprite. Right, so let's actually change it and save it. So let's say we add something here, something like that, and then we copy those first 5 bytes back into here with a space, and now we have changed the ship. So I mean the asteroids. All the asteroids now have this weird shape next to them. All right, so let's undo that because it doesn't make it look any better. So I points to rock, which is this data, and then we do sprite. We've seen that before with the ABC example. We sprite at X is our random number that we just generated. V2 is our Y position. So that's this one. That's that 0 that we loaded up here into register V2. And then we draw 5 bytes of data. So that's these 5 bytes of data, resulting in 5 lines of asteroid being drawn. Alrighty. So we're almost through. We're more than halfway through this game. If V3 key, then V0 minus X3. So minus equals. What does that mean? This feels a bit more complicated. We've seen an if up here as well. Ifs and elses and all those kinds of things are again something that Octo introduces, because in CHIP-8 it's much more basic and actually harder to work with. So Octo helps us here to actually gives us constructs like if and else. What this does is if the key that is referenced in V3, so that is this thing, remember, key A, that is what we loaded into V3 all the way up here. If that key that is referenced in this register is pressed, then and only then will we do this. And the same with the other direction. So if the other key, or key to the right, or D key, is pressed, then we add 3 to V0. Now V0, if we remember correctly, was our ship's X position. That's this thing. That was also initialized up here. And it is where we are drawing the ship. And then finally, we point I to the ship sprite, the thing down here that we just looked at. We sprite that to the screen at the coordinates of the ship. So the V0 that we may or may not just have updated. And then V1, which is the value that we loaded here. And we draw the ship for 3 bytes, because as you can see, this is just 3 bytes and it looks like that. And then you may be thinking I'm missing something here. We were missing something. There is no way to detect if the ship actually crashed into an asteroid or not. And even though that is clearly working, I mean, if I run into an asteroid, something happens, right? The way that works is Sprite has a bit of a side effect, so to say. Every time you draw a sprite, the sprite instruction will see if there was already something on the screen there. So if you're erasing something, and it then sets the VF register, like I said, that is the flag register, it sets the VF register if 2 sprites like overlap. And that is a very interesting quirk of CHIP-8 that makes it relatively easy to make these types of games where you just want to check for collision somehow, but you don't want to write all the code for it. All right, so what John does here is if VF, so our flags register, is 0, then all is fine and we did not hit an asteroid. Then again, so we jump back up to this loop instruction here, right? So if VF is not 0, if it is 1, it means we collided with an asteroid and we are game over. So it's that easy. And then the final thing that happens here is VF, or flags register, is set to key. And what key does, this key is different from that key in that sense that this doesn't wait. It just checks to see if this key is set, is pressed. Whereas this key actually waits for the user to press any key, and then it returns the value of the key that was pressed into a register, right? In this case, VF. So you can use that for like turn-based games, for example, if you're doing like a chess game or something, where you're just waiting for the user to input a coordinate of a chess piece. You can just say v0 is key, v1 is key, and then you have like two values that you can use in your program. But in this case, we're only using it to like introduce a delay until the user presses a key. And then when the user does press a key, we jump back to main, which is up here. And the entire program just restarts. It loads the registers again, resets everything, clears the screen, and then goes back into the loop that makes everything tick. So that is like 80% or so of what CHIP-8 is. There's a couple more instructions. I recommend looking at the manual in Octo for that. But basically, I think you understand pretty much enough now to make your own thing for Octojam, for example. Don't forget to join in the fun and make something cool for Octojam. And this is the game that I just showed you on the Thumby way back at the beginning of this video that I made 2 years ago. Oh, it makes noise. Let's mute that. There. This is the game that I made, and it's a 3D maze crawler thing with coins and vipers, and it is still very simple, very basic, but you can open the door this way, and then you can move out. It's still very basic, but that is the fun of CHIP-8. The fun is in making things that are simple and basic, and that go back to the retro computing vibe from the 70s or something. Right. And one tip that I have is to take a look at the examples in Octo, because there's a couple of different programs here, some that make sound and music, some that just make something crazy appear on the screen. Learn from example and see how other people manage to do things. And this game, for example, is an excellent game. Just take a look at all the ideas in these games. Use your own creativity and your own skill set and make something awesome. I hope this, let me switch to the camera. I hope this inspired you to make something of your own, and I hope it helped you get started in your CHIP-8 journey. See you next time.